Hello and welcome to the 22nd lecture. Today we are going to talk about the non-abelian Higgs model. Basically we are taking the same thing as the abelian Higgs and changing the gauge boson from the abelian to a non-abelian one, and that makes the Higgs field, the scalar field, a multi-component field. So we will have our Lagrangian written over here. So this looks exactly the same, except here Fa mu nu, Fa mu nu is there, where A runs from all the number of gauge bosons that we have over here. D mu phi dagger phi minus of mu square phi dagger phi minus lambda phi dagger phi whole square. This term the potential term looks exactly the same. So in terms of the phi mod, it's going to behave exactly the same. For example, for minus mu square greater than 0, that is to say mu square being negative, the classical potential has a minima when phi mod is 0. Okay, that is the symmetric case, and quantum mechanically that is written as vacuum expectation value of phi is 0. Okay, so that will be equivalent. So this is a classical statement and this is a quantum statement, but we are talking about the minima of the classical potential. It's important to use the phrase classical potential over here because we have not yet considered the corrections, quantum correction, the loop corrections, and that loop correction will indeed change or modify the classical potential. And for the other case, when minus mu square is less than 0, so to say mu square is positive, then the classical potential has a minima when vacuum expectation value of phi dagger phi is v square by 2. The reason for writing this is that phi dagger phi will always give me a real value, while phi is a complex number, a complex field. So vacuum expectation value of complex field is expected to be a complex number, and saying that that is v by root 2 is kind of saying that I'm already making a choice that which part is real and imaginary. Here I don't want to commit to that. So here in classically I would say phi mod is equal to v by root 2, where v is just mu square by lambda. Okay, so here we have seen this in lecture 20, how to expand this Lagrangian up till here, and actually phi dagger phi was also written in the case to give the mass term. Okay, so there is nothing in this Lagrangian which we do not know already in the component form, and in the component form phi dagger phi is just sum of all these guys, all the phi dagger I phi i's, because phi is the n component guy over here. So here that's what I'm saying is the n dimensional representation. Now just to remind you of the how this Higgs mechanism is done, the computation with the Higgs mechanism is done, that v phi dagger phi is what gives you a non-trivial vacuum, that is the minima at a minima of this potential is at some phi mod v by root 2 for v not equal to 0. So this is what the job of potential is. Something the potential is such that it gives me this. That's step 1. Then d mu phi dagger d mu phi, okay, that gives the mass for the this gauge boson through this phi dagger phi. Actually I should have said phi dagger phi. Okay, it is phi dagger phi a term. So anyway, it is written symbolically, not all the indices are matching, so we just should determine mu term. This is a 4-point interaction term is what leads to the to this mass term, and the details of computation actually depend upon what is the symmetry algebra and what representation that scalar multiplied belongs to. Okay, so those are just details of the computation, and we will perform some details of the computation in this particular lecture. But before we move ahead, it is very important to note this point. It is possible to choose a representation for phi such that the symmetry breaks only partially. That is to say, some gauge boson remain massless even after the symmetry break. Even after this Higgs this mechanism, some gauge boson will remain massless. So we'll look at this example, but first we'll look at the example when you give the wave, it gives masses to all the gauge boson. Okay, the example is SU2 is my gauge symmetry, so my A mu A is basically A mu1, A mu2, A mu3. FABC is my epsilon IBC, where epsilon 1, 2, 3 is set equal to 1. Epsilon is the Levi-Civita symbol with 3 dimensions. And so this is my gauge symmetry. That's the first thing I need to choose for detailed calculation. And for the second thing, I need to say that under which representation of SU2 the phi belongs. And phi we choose here to be a doublet. So phi is the some upper component and the lower component, and I can write the real imaginary part of the upper and lower component. So basically there are 4 scalars. Okay, and let phi 0 x be 1 by root 2 times 0 v. So v by root 2 is sitting over here, and if you do phi dagger phi, it will give you v square. Okay, so I just, for simplicity, I am choosing the lower component to have the actually not simplicity, both are equally complex or simple. Okay, there is no difference in the computation steps of the computation. So just for being explicit, I'm saying let there be a down guy, okay, with a vacuum expectation value of the phi x when the potential is minimum. So I have phi dagger 0, phi dagger phi 0 is v square by 2. Now let phi be written as phi 0 plus some phi prime of x. So phi prime of x, this is exactly what we did for the abelian case, so we do the same thing. So here phi dagger phi will be written as phi prime dagger phi prime. This is the first piece, okay, and then phi 0 dagger phi prime plus phi prime dagger phi 0, and then phi 0 dagger phi 0. So the phi 0 dagger phi 0 is written simply because it's v square by 2, not an issue. And phi prime I just again write as a phi up and a down component, much like what I wrote over here, but I'm using now it for phi prime, not the full phi. Okay, so when you do this, then phi prime a dagger phi prime, which is appearing over here, becomes phi u dagger phi u and phi d dagger phi d. Okay, so this is quadratic piece. Now phi 0 dagger phi prime, it just gives you 1 by root 2 v times phi d, and phi prime dagger phi 0 will gives you 1 by root 2 v times phi d dagger. Okay, so these are the Hermitian conjugate of each other. So when I use this, so first piece it just becomes phi u dagger phi u, second piece, and it has 2 pieces plus phi d dagger phi d. This guy is coming over here, and these two terms basically becomes v by root 2 times phi d dagger plus phi d. Now you can already say phi d dagger plus phi d by root 2 is I can define to be another scalar. Okay, but let me carry over this complicated expression throughout, and here the last piece is here. Okay. So this is my phi dagger phi that appears in my Lagrangian, and next piece that appears in the Lagrangian is phi dagger phi whole square. So the way I am starting is from the right hand side here. So the square of this guy is some constant, and usually these constants I won't care for much when I'm writing the final term in the Lagrangian, because they don't have any dynamics. Okay, then the cross term of this constant term with other guys. Okay, so this guy with this guy will give you a v cube by root 2, a phi dagger d plus phi d, and this guy with of course time 2 is there, so that's why this 2 is gone. Is that so? Have I done it right? Yes, sorry, yeah, it's done right. So this with this cross term is this piece over here. The 2 cancels and only root 2 survives. So it is 2 times, so if this is my a and this is my b and this is my c, so what I'm writing is in square, this c square is written here, and 2 times bc is written over here. Okay. Then this is 2 times ac, so this thing with this, but I still write phi prime dagger phi prime just for making the expression short. Okay, so that all the things with this guy gone. Now I will have this guy square, which is written over here, and then this guy interference with this guy, which is 3 scalar meeting here, and then square of this guy, which is a 4 scalar meeting over there. Okay, so now what I need to do is multiply by minus mu square the phi dagger phi, and multiply with plus lambda the last piece, and add up. And then I say I don't care for the constant pieces. So first thing I care for the non-constant piece is when the fields are linear. Term is linear in the field. So I take phi dagger d phi d by root 2 as a common thing. So and which is appearing here also. So what multiplies over here is minus mu square times v comes. So v is taken common, and here lambda times v cube will come. Okay, so I take v common, so I get minus mu square plus lambda v square, and this thing in bracket is 0 because you see my vacuum expectation value v is equal to mu square by lambda. So multiply lambda on this side and bring mu square to the left side, it will give me 0. So v square lambda minus mu square is 0, which is what's sitting over here. Okay, so linear term in the field, that turns out to be 0. Okay, now let's look at the term which has phi dagger phi, phi prime dagger phi prime. Okay, so in here I will get phi prime dagger phi prime from the quadratic piece will come with a minus mu square, and here it will come with a lambda times v square. Okay, so again this term will cancel, so square of phi prime dagger phi prime, which means that phi u dagger phi u and phi d dagger phi d is simply gone. Okay, these pieces do not appear, so looks like the mass term for this term is not there. But then I do have so this is another quadratic term that will be there, which is this, which is phi d dagger plus phi d whole square. Okay, so this was hanging over there, and this term times lambda is the only quadratic piece that survives in this Lagrangian, giving mass only to this guy and mass to all other guys will not be there. And then 2 times lambda this cubic piece, which is not there in the quadratic, and lambda times this quartic piece, which is of course not there in the quadratic. So this is all the field dependent pieces that I have written. And obviously here what we see that if I write phi prime as a phi u phi d, and then much like the real and imaginary part that I have written earlier, then phi d dagger plus phi d by root 2 is nothing but phi d1, which is the real part of phi d, and this is what appears with the mass term. And so this is my Higgs boson, that is massive. Okay, it is 2 lambda v square, which is 2 mu square is the mass of this field. Okay, now all other fields are massless, they are all Goldstone boson. So here I'm writing them into the real and imaginary part, and still I see that masses for everything else except the real part of phi d prime, phi d1 is 0. Sorry, phi d1, everything other than the phi d1 doesn't have mass term, which is means u1, phi u1, phi u2 and phi d2, all of them are massless. Okay, so all the massless gold boson can be absorbed into the gauge field A mu by gauge transformation. And perhaps this is this representation is not the best way to see it, because this takes the real imaginary part. To see this explicitly, we have to go for the polar representations. Okay, and steps are exactly same as the u1. So here what we saw by looking at the potential is what are the massive guys, what are the massless guys, how many are massive, how many are massless, and all that we figured out. And then we are trying to see that what is happening over here in this particular thing, that how do I write can be absorbed now I'm going to look for the d mu phi dagger d mu phi, which is responsible to give me the mass. So d mu phi dagger d mu phi, in sticking to matrix notation as much as possible, this is the term, the last piece, g square times phi dagger a mu phi. TAs are sitting all over here in between. This is the guy who is responsible for the mass, so I'm going to write this explicitly. So g square phi dagger a mu blackboard phi, so a mu phi in bold can be written as g square phi dagger ta tb phi and a mu b. Okay, now for phi being a doublet, ta is equal to just sigma a by 2, the Pauli matrices, and this a mu a can be written as 1/4 of identity matrix a mu a. Okay, so this is a property of so 1/4 is because the sigma by 2 is there, and the rest is the property of the sigma matrix, that sigma I, the sigma I sigma j plus sigma j sigma I is 0. So when I'm doing this summation, when a and b come in reverse order and unequal, they cancel, and when they're the same, they just become sigma square. Okay, so that is what sigma square is. All sigma squares are identity, so that's your two-dimensional identity matrix that is sitting over here. So it basically becomes this expression, and that expression is now, this identity is sandwiched between phi dagger phi. I should say, yeah, that's general one. Okay, but to get the mass, what I need is only the phi 0, right? So this is the most general term, but for generating the mass I can replace here phi with phi 0. So I'm interested here in phi zeros. Okay, and when I put the phi zeros over here, so it basically becomes phi 0 dagger phi 0, which is v square by 2. Here is set t square, and 1 by 4 comes from this oval matrix. So I just rearranging is half of gv square, gv by 2 whole square, and mu a, that means mass of each of the gauge boson for all of the a is gv by 2. This is the mass term. Okay, and all the extra factor 2 came here compared to the abelian case is because of this by 2 definition of sigma. Okay, now this is all right in this Cartesian choice. Now what is called the unitary gauge choice, where I write phi as exponential times some phase factor, which is again written as tau a sigma a by v, and tau a by 2 sigma a by v, xi a by v, sitting in the exponential, and here I have 0 plus v 0 and v plus eta by root 2. This is my parameterization of my massive scalar field. So here is the massive scalar field, and xi a's are 3 massless Goldstone boson. Okay, so this is just a polar full matrices are sitting over here. Now what do I have to do over here? So follow the step is do a gauge transformation, phi going to u times phi, such that this guy cancels out. Okay, so and phi dagger phi will just be these pieces, and a mu becomes here b mu. So d mu phi dagger d mu phi will have a piece which has g square phi 0 dagger b mu phi 0, and all the potential terms have only eta and no xi, so that is trivial that they don't appear, their masses are 0, and the b mu has already absorbed all the xi's by doing this gauge transformation. So mass is the same thing, doing a different coordinate system. So mass of each of the gauge boson is gv by 2 for each a. Okay, now before we go to the case of partial symmetry breaking, we need to note is that the mass term is basically written as g square phi dagger 0 ta tb phi 0 and some ba mu and bb mu. Okay, some gauge transformed gauge bosons. And here I say that let G be the original Lie algebra to which all the Ta belongs, so that Ta Tb commutator is I times FABC TC, and all of them are sitting here. Let H be a subset of G such that it has same property, that it's a how do I say, there is a sub algebra, so it is closed under this commutator also. Okay, so I'm only taking those elements that into this set that appear on the right hand side for the commutator. So I can always look at a subset which is again satisfies all the property of being a Lie algebra. So of course, if the Lie algebra is big enough, it can contain a sub Lie algebra inside it. Now what I have to do is that if Ta phi naught is 0 for all Ta's in the sub algebra, then what happens that corresponding gauge bosons do not get mass, because what happens, this let's say Tb acting phi naught is 0 and this entire term is 0. So since Ta and Tb are Hermitian conjugate of each other, so Ta acting on phi naught is same as phi naught dagger Ta being 0. Okay, so either A kills to the right or it kills to the left. Okay, so if any of this thing is 0, then the moment that guy appears, Ta appears over here, then it will kill this term. Okay, so I will never have masses generated for those particular gauge bosons after doing whatever gauge transformation. Gauge transformation remains the good symmetry because mass term for those gauge bosons are still not generated. Okay. So let's look at an example for that. So partial breaking of SU2, we look at the phi belonging to j equal to 1 representation, that is a triplet. So phi is phi plus, phi 0, phi minus. This is much like the pions in isospin triplet representation. Okay, and phi dagger can transpose of that can be written as phi minus, phi 0, phi dagger. So when you take a dagger, it changes to its complex conjugate, but what we have is a phi plus and phi minus are Hermitian conjugate of each other. in this representation. So what happens, and of course phi 0 dagger is phi 0, so this is a real field and these two are complex field and Hermitian conjugate of each other. So I basically have one complex field and one real field, giving me 3 scalar degrees of freedom over here. Okay, and for spinor, for this representation, you can check in any quantum mechanics book. The SU2 representation for a triplet is, you may not have this normalization in that book that you might be using. I'm choosing this normalization for a different purpose, which is to say the trace of TATB is normalized to this value. So for that I am choosing this. So this is T1, T2, T3. T3 is the diagonal guy. Okay. Now for symmetry breaking, I have phi dagger phi equal to V square by 2, and phi dagger phi, if you write, is phi minus phi plus phi minus plus phi 0 square is V square by 2. So obviously I can choose this phi 0 in several ways, and I have to make sure that they are self-consistent choices. So choice 1, which is called phi 03, I name it. It will become obvious why I am giving index 3 over there. So it has 0 and entries in the first and third, and middle entry is V by root 2, and all this normalization is chosen appropriately. Now you see, that is to say, all the charge guys don't have charge guy means that charge it is a charge scalar, complex scalar don't have wave. Is the real scalar have wave? That's my first choice. Now if I want to give wave to the complex guy, then real it is like real plus I imaginary, and here real plus I imaginary. So I give wave to the real part, then I get V by 2, V by root 2, V by root 2 over here. Okay, so and 1 by root 2 comes from the fact that it is already a real field over there, so that extra factor of root 2. So here wave will be V by 2 and V by 2. Okay, I call it the choice 2, phi 02, and so here I'm giving wave to the real part. Now if I give wave to the imaginary part, I get IV by 2 and minus IV by 2 with a 0 in between. So these are the 3 choices one can work with, and let's just see what happens in these 3 choices. So choice 1, which is phi 0 is phi 03, then what happens here is this T3 acting on phi 03 is 0. So you can just check it here. This is the central piece, and here the middle row is all zeros here. So T3 acting on this guy is 0. So in my expression for mass, I will never have mass for A3 mu, but I will have mass for A1 mu and A2 mu, which will have be GV by 2. Okay, I just did the computation using these matrices, explicit matrices. I'm telling you that it is GV by 2. Okay, and choice 2 would be that phi 0 is phi 02, and here the T2 acting on this is 0. You can again check that T2 has this I and minus I in the second row, that gives me 0, and first and third row directly gives me 0. Okay. So T2 acting on this will be 0, and that's the reason it's called phi 02, and here the choice 1 is called phi 03 because T3 acting on that was 0. So here accordingly A2 will be massless, and A1 and A3 will have mass GV by 2. And third choice is that phi 0 is phi 01, where T1 acting on phi 10 is 0, leaving us A mu 1 being massless, and A2 mu and A3 mu will be again massive GV by root 2. Okay, so I'm not going to go much into detail for the algebra, is just I'm showing that the condition for having the mass was that this term is giving me mass, and condition for having 0 mass despite giving the wave is that this T matrices basically kill that wave. Okay, so wave is killed by that action of the T matrix, so that corresponding gauge boson will remain massless. It will not appear in the expression at the quadratic level or even at the linear level. So you cannot have B1 and B2, because if it is B1 is supposed to be massless, then T1 acting on the left will give me 0 still. So whatever kills it, it cannot be either on the left or on the right, so that just goes away from this term. That remains completely massless. There is no appearance of that in such interactions over there. Okay, now the details of algebra for these things is trivial enough, and so that I am not showing explicitly. I wrote the T1, T2, T3 over here, and I showed how it becomes 0. So 0, it's easy to show, that's what I argued, but it's important to know that whatever is non-zero, what it is. Okay, and for that you need to do is explicit stepwise computation, and that would be your one of your homework that I will type and send. So quite a few lectures I have been collecting problems for homework, and I'll type all of them, and you will have one biggish kind of homework to practice this thing. And again, I'm not going to go too much details of this, either the Goldstone bosons and Goldstone theorem and the symmetry breaking, more than what I have done, is because it's done in enough detail in particle physics course by Bishwarup Mukhopadhyay. All the guys who don't have particle physics as one of your lecture, I request you to get the links for the video from your classmates and have look at those lectures, and notes also you can get from your friends. So in the initial lectures, many of those students who were not doing QFT but doing particle physics were asked to attend my lecture to do that, to appreciate the fermion part, because it was not done for your batch. So I had to do that fermion part anyway. For this course I had to do, but I did it in more detail than what was required for this course. I believe that I can trust Bishop's notes and his quite detailed analysis he has done for the Goldstone theorems and all that, and for the abelian and non-abelian symmetry breaking. And he will finally do the SU2 cross U1 symmetry breaking, and there you will see there are 4 gauge bosons, 3 from the SU2 and 1 from U1. All of them apparently get mass, but you will see that the wave is the vacuum expectation value is still killed by not any one generator but a linear combination of generator, and that the gauge boson corresponding to that linear combination will still remain massless, and that becomes the photon. So I am not going into details of that. That will be done in particle physics course as far as this lecture is concerned. So with the help of some of homework and this notes that I have here, you will be able to appreciate the mechanism of gauge symmetry breaking. And I must repeat this, that quantization of these things one has to be careful about after the symmetry breaking. Okay, and renormalizability, when we come to that, everything was proven explicitly for these cases, this symmetry breaking Lagrangians and all that, and I think early 70s people have proven all these results. Okay, so when I go to renormalization, I will briefly mention that, but it's important to know that quantization of gauge field will be issue that one has to be careful about throughout, and it becomes more natural and trivial when we do it through the path integrals, which is what we are going to start next. In the lecture 23 onwards, we will have path integrals first basically for the quantum mechanics, then we move to the scalar fields, then we move for fermion fields, and then we move for the gauge bosons, and then we'll do some analysis over there. So with this I sign off from this lecture. Next lecture will be path integrals.